Okay, everyone. So in this series of lectures, I'm going to talk about the postulates of quantum mechanics. I would say that, in effect, this is the rules of the game. Right? These are the basic ideas that we'll use to study all the problems in the remainder of the course. They're described in Atkins 7b and 7c, and I tell you at the outset that this isn't a formal list. These aren't sort of written in stone someplace, but I've adapted them from Atkins and some other places in a way that I hope will be helpful to you. There are 5 of them, and I've written them all out here. I'm not going to read them, but what I would encourage you to do is to look at the handout in the supplemental materials page on Canvas. I'll put these all up, and I hope that's a good reference source for you. So away we go. We're going to start working our way through these. But before we do that, I just wanted to point something out to you. If you look at some of the postulates, you'll notice that a number of them have mathematical equations. And you might start to look at these equations and ask yourself, what in the world is going on here? What kind of chemistry is this? And that's a fair question. So at the very outset, I wanted to give you an example, at least of one kind of chemistry question that we can answer using quantum mechanics. And so here it is. Here are 3 conjugated polyenes, anthracene, tetracene, pentacene. These things basically have the same structure, right? These fused benzene rings. Reactivity is fairly similar, but you'll notice they exhibit these very different colors, right? White, orange, black. Why? What's going on with these systems that they exhibit these different colors? These are the types of questions that we'll be able to answer, hopefully, at the end of this unit. Okay, let's dig into the postulates. Postulate 1a says that the state of a quantum mechanical system is completely specified by its wave function, psi of r and t, which depends on the coordinates of the particle and on time. So this basically introduces the concept of a wave function. Wave functions are given the Greek symbol psi. Pointer options, let's see if I can do this. So this is the Greek symbol psi, sometimes called the devil's pitchfork. And what is a wave function? Well, I listed some definitions for you here. Macquarie, I said Macquarie, but this is Atkins actually. Atkins says that the wave function contains all of the dynamical information about the system it describes. Okay, might mean something. If you were to look it up in Wikipedia, it's a little bit more abstract. A mathematical description of the quantum state of a system corresponding to some maximal set of commuting variables in a given representation from the available degrees of freedom. Also very correct, but probably less meaningful to you, right? It's not clear what in the world what that means. What I would tell you is that the wave function is the physical entity which describes all of the information about a system, right? Once you know the wave function of a particle or a system, you can figure out whatever you want. So equations of motion, energy levels, where it is, where it's going to be, all of that sort of stuff, right? The wave function is what we're trying to solve for in quantum mechanics. Where does the wave function come from? Well, see postulate 1b. Postulate 1b says that the wave function is defined by the Schrodinger equation. The one-dimensional, time-independent version of the Schrodinger equation is here. Negative h bar squared over 2m. A second derivative, v psi equals e psi. If you're looking at this equation, it might look weird to you. It's not a differential equation. I guess it is a differential equation, but it's also an eigenvalue problem. Right? And we'll talk about exactly how you solve this. But you need to be aware of it. And the one thing I would point out to you in this is there's one new variable, which we haven't seen yet. It's this guy. Right? This is called h bar, right? H bar equals h divided by 2 pi. H is Planck's constant. You could look that value up and you'll see that it's 1.055 times 10 to the minus 34 joule seconds. H bar will also show up throughout the course. So we'll talk about this equation. It's the one equation really that we'll study, and the one equation that we'll study in the course, and we'll get into it. So that's postulate 1. It defines the wave function and tells us where it comes from. Really quickly, I want to tell you briefly about Erwin Schrodinger. So this is who that equation is named after. He was an Austrian scientist, one of the founding fathers of quantum mechanics. He proposed the Schrodinger equation in 1926. Again, this is extremely important. This is his grave in Vienna, and you'll see that he has the wave function psi on his gravestone. 7 years later, right, he won the Nobel Prize in Physics. And you may not be exactly calibrated, but that is an incredibly short period of time, right? People recognized the power of this equation and its importance really, really quickly. And so he won a Nobel Prize in Physics. And actually, towards the end of his life, he actually became interested in biology. And specifically, he became interested in the question of how life formed on Earth. And he had what at the time was a really crazy proposal, which is that he thought organic matter might have arrived on Earth from cosmic sources. It could be a comet, it could be aliens, it could be whatever. And at the time, this was sort of ridiculed. There's no way that this might have happened. But actually now this is a really common area of study, right? What are the sources of organic matter on life? It very well could have come from a comet or asteroid which struck the Earth, and people are actively looking at this. So once again, Schrodinger was well ahead of his time. All right, that's postulate 1. I'll stop here and I'll see you in the next video.